Hello, how's everyone doing today? Great, awesome. Okay, so we can start with our next talk. It's by Jason, and oh, I love this talk title. If an async IO task fails in the woods and nobody's around to see it, does it still page you at 3 a.m.? Right, over to you, Jason.
All right, welcome to my talk. This was the longest title I could think up, but if it helps, you could refer to it by a handy acronym, IAT fit woe, ATC dis by 3, but which that should be less cumbersome when you want to talk about this talk in conversation later. I actually wanted to see what that looked like on the, I guess we don't have time for that. I'm currently a production engineer at Meta. I've contribute irregularly to CPython and various other open source projects. And I've been writing software for a while. I've spent 7 years writing C code and then 10 years writing Perl. And basically I started writing Python when I started at Facebook in 2011. So I've been involved in Python development for 10 years, a little bit more. At Meta, I drove the Python 2 to 3 conversion way back when, just so I could use async IO in production. Though back then it was still called Tulip, and we were still on before 3.5. And when you're a pioneer, you have to ford a lot of rivers, and you have to make do with whatever you can build yourself. So we had rivers that had to be crossed before appropriate bridges had been built in the standard lib or PyPI. So I had to build them, or to solve problems like async unit tests, async context managers. We needed an exit stack. But fast forward to today, we have hundreds of backend services written with async IO. There are tens of thousands of people authoring Python commits every month at Meta. So I have seen lots of code. I've seen the good, I've seen the bad, and I've seen the ugly. And in this talk, we're going to cover the ugly in very humorous detail. Things like nested event loops, bad async IO bootstrapping, anonymous tasks, calling coroutines in the init method, bad signal handling, ignoring cancellation, and not using timeouts. So on the subject of event loops, now this is mostly for library writers. You have existing callers, you're not an async def, but you want to call a coroutine. This seems very simple. Oh, I'll just hit the default event loop and I'll run it to complete. Well, the problem comes is that you have some caller way up in a call chain that you're not even aware of that's already running the loop. And they get an exception about the loop already running. And because you would have to change a whole bunch of unrelated functions outside of your own project to have async def variants, you figure it's just easier to hack it. So you decide to pause the existing loop and use your own loop. So this pattern is called the nested event loop. You basically trick async IO into thinking that there are no event loops running so that you can create your own and start it while you block the current one. The example above is obviously shorted, and we'd have some mini slides to go into detail, but it's really a dirty hack. And it has some very bad unintended consequences. And will probably get you paged at 3 a.m. because the service owner is seeing timeouts in their event loop once you stop blocking it. Look, I've seen this kind of logic used at Meta, and people still try to do crazy shit like this. Because we all know writing quick and brittle, unmaintainable code is better than taking time to do it correctly because it just seems easier. Well, it's easier now, but in the long run, it's going to be very hard. The first thing is that this is completely unsupported behavior. It requires you to reach into the guts of async IO to make it work. And the next thing you will find is that the original loop has things scheduled on it that you were not aware of. And those things have timeouts. And those timeouts will get expired because you have blocked its event loop. The last one is you will end up having tasks on the new event loop that you had created, and they will throw some strange stack traces when you'd have to close up your own event loop. And in the future, you might have other work that gets somehow added to this sub-loop, and you might have loops within loops nested very far down, and it'll be very hard to reason about what's going on. I've given up trying to help people when I find them doing this, and I just like point them in the right way. But the more magical your Python code gets, the harder it will be for you to support it. Understanding what it's doing when something does go wrong is just a wasted effort. So the solution is just to use asyncio.run. You may say, well, doesn't asyncio.run have the same issues as we had before? Well, yes, it does. But it lets the caller easily put it into a different thread using an executor, because it creates a new event loop instead of assuming that there's a default one, which is not true on threads other than main. And that exception thrown is a good thing. It lets the caller know that they need to put the function in a thread pool executor. Or you could do it for them if you happen to live in a giant monorepo shared code base like Meta, because you need to land your own changes and you don't want to break their tests. Now, the best solution, but it's not always practical or possible, is to provide an entire async def call chain from their code to your code and maintain a separate blocking call chain that used to exist. It sounds daunting, but that's probably the best solution. So some tips is you only own the event loops you create. Respecting ownership means that if you do not own it, you don't mess with it. Like, you don't come to my ranch and mess with my goats, and I'll afford you the same courtesy. A core tenet of Python is that we are all consenting adults. We don't need the language to make us behave or respect each other's privacy. And in the case of event loops, don't stop it. Don't start it, don't block it, just leave it alone. You can do normal stuff, but you definitely don't set up a magic sub-nested event. This violates the #1 rule of async IO, which that you're just now going to hear about it, because I made it up this week. You are not allowed to block the event loop on purpose. Sure, people block it all the time out of ignorance, but when you do it on purpose, that's malicious intent right there, and it makes you a bad person. But, well, you're maybe not a bad person, but you should feel bad. So you should be using asyncio.run, and ideally only ever have one event loop. If that's not possible, have one event loop per thread. But you should never have more than one loop on the same thread. It's just madness. Also, let your callers decide what to do. They have more context than you and about the event loop and maybe what might be scheduled there. And they have the ability to put in an executor. You don't have that from a blocking call. Now let's look at the bootstrapping async IO and why it's important you have clean async bootstrapping. Bootstrapping is the process of starting up the event loop, scheduling the initial work, and also concerned with handling the results and handling cleanup and taking care of signal handling so that your application can terminate sanely. You've probably seen code like this in the past. I've seen it all over the place. It's a holdover from a pattern before we had coroutines and before we had async IO run, and it was encouraged that people use callback style async IO. So this is super old. It's terrible. You're in and out of the loop. We start the loop, we run it, we get some value, go back into the loop, we create a task, then we run forever. Well, we don't ever actually stop the loop unless somebody stops the loop. If that task died, we're still running the loop. And if we somehow do stop the loop, we have to handle our own cleanup. So we have to cancel the task, and then we have to run the loop again. And then we finally close it. So that task, while it has a name, it might as well be anonymous. We don't ensure that it stays running. This might get you woken up in the middle of the night to find that your running service is actually doing nothing. This is a kind of a maintenance nightmare. So even if you do get your task canceled, you have no knowledge, or basically you can't ensure that the callbacks, if there are any callbacks on it, actually get run before you complete and run until complete. The solutions pattern is easy and much cleaner. Like the last issue, the solution is asyncio.run. It handles all the crazy bootstrapping, cleanup like cancellation of tasks, and some basic signal handling. And it's just less code and easier to read. Now we're doing pretty much the same work, but we basically take a coroutine and we do all initialization and pass it to asyncio.run. If that very important task, some server that we had before, if it fails, the code just exits like it logically should. And since we're talking about tasks, let's look at the problem of anonymous tasks, or what I call set it and forget it pattern. It also applies to daemon threads. Unlike an infomercial kitchen rotisserie, tasks should never be created and forgotten about. This is exactly the kind of thing that gets you paged at 4 in the morning. Turns out that something important happens in the do something coroutine, and it has been printing exceptions all night. But because we didn't do anything with the tasks, nobody noticed. They just get printed to the standard error, and nobody noticed till 4 in the morning until it started breaking other things. You should have some mechanism to ensure that your tasks are inspected when they have exceptions. Your unit test should look for these unhandled tasks. The solution to this is simple: use asyncio.run. Okay, that's a joke. Not everything is solved by asyncio.run. It can't solve all your problems. One possible solution is the nursery from Trio. I don't know the origins of the name, but we can generally reason about how it should work. We don't let small children just wander around unattended, and we put them in a nursery so that we can watch over them and take care of them in case something bad happens. Now, don't get the idea of killing all the other kids when one kid has an issue. That kind of gets dark, and it mirrors the disturbing terminology we use when we talk about the POSIX process model about killing children when their parents die, and sometimes there's zombies involved. To get back on track, the gist of this idea is you have this failure domain of tasks. If a task in the nursery dies for whatever reason, the other tasks are canceled. An application-wide feature domain is useful for important tasks that, for your service, that if they failed for whatever reason, would be really bad. You can get this functionality in asyncio using the AIO nursery or the later package from PyPI. Though later calls them watchers, they basically have the same goal. So you might ask, well, I don't care if the task fails, it's best effort. I'm logging or doing something like that. So sure, if it fails every once in a while, maybe that's fine, but what if it started failing every time you called it? Is that still best effort? You should have some mechanism to ensure that not all these best effort activities fail. Maybe set some kind of SLA. Like if you start failing a certain percentage per hour, maybe you should do something about it. Or go ahead and set your alarm for 3 a.m. so I can call you. You might say that you're just using tasks for this abomination. So this is example I've seen in talks, and I've seen this online, is we have this bound queue, and we're putting an item on it. And they're like, oh, I don't want to get blocked, so I'm going to put that in a task. So I've seen this pattern talked about. Like, what the hell are you actually doing? Because this is so much more performant, just having an unbound queue and using put no wait. Like would you rather unbound memory growth potential or unbound memory growth potential and slow ass event loop cycling through an unbound list of tasks, which has in effect become a second queue, which if you know anything about queuing theory, you don't do secondary queues. But this one secondary queue is way more expensive than the original queue, because the bigger it gets, the slower your event loop gets. Because your event loop has to cycle through all the tasks to check them if they're ready. So if you're going to do something like this, then just use an unbounded queue, or use the put no wait. But if you're going to use a bounded queue, use it for what it's supposed to be for. It's supposed to be for flow control, so you can get back pressure. You can know that the queue that we're working on is filling up. Maybe I should report to the user that we're overloaded. Let's move on. So calling coroutines from init. People always seem to want to get in the situation where, like, I got to call this coroutine from my init method. I see code like this, and I personally think, do you hate me? Like, are you doing this on purpose? Like, so by doing this in init, you have barred me from using asyncio run, which, according to this talk, you'll know is my favorite thing in the world, which you should be using, by the way, since it creates its own event loop, that anything you produce or start here is in a different event loop. Some people use that nasty magic nested event loop that we talked about before, and it has all the same problems, and it's weird. Or they create anonymous tasks, which we just got to finish talking about. The problem with these patterns is you are doing some kind of async activity in a place that was not designed and is ill-suited for that task. Like, what are we really trying to do here? Like, any I/O inside of an init method is bad design. Good init methods should not block or affect any state outside themselves. So don't do this. You don't need it. There are better alternatives. The solution is the async context manager to initialize any async state of an object. By using an async context manager, you have a method that is well suited for initializing async stuff. And as an added bonus, you have a well-suited method for cleaning and canceling your async stuff, because they're coroutines. That's what they're made for. And on the subject of using context managers, I have seen code like this you get a random package somebody's downloaded in PyPI and they want you to help them get it running. And you have to go read through their docs and you have to find what they've decided to name this method that you have to run for it to work. Well, there's no conventions. This method could be named anything. Here it's like, oh, let me go read your docs again so I can see what this thing's gonna be called. But then you sometimes have to worry about cleanup and you have to go find out what that's called. Though with an async context manager, there's a better pattern. It's the same amount of work, except that the maintainer of the better async web server can do it for you. This pattern is less error prone. It uses less of your own headspace to keep track of. The API is defined by a PEP, which means it's well defined and part of the language. You'll learn it once and it never changes. Well, hopefully. The async context manager and context managers in general are pretty awesome. they're like the perfect system for writing like a plugin or extensions. No matter what my object does, everyone already knows how to enter its context. They know how to clean it up. It's built into Python using the with statement, or in this case, the async with statement. So let's move to signal handling. Every application needs signal handling, especially async code. Async.io run, which I love to talk about, gives us some helpful defaults for Control-C, and which is aka sigint, but you probably will need more. This is essentially the signal handling example in the async.io docs. I've shortened it and I've cleaned it up because I didn't like what they were calling functions. But basically, we have our main method, we get the loop, the running loop, the correct way, and we set the sig init, we set the sig term, the first one being Control-C, and we add the signal handlers, and we do some partial magic so we can pass it the loop and what the signal was. And then in our handler, we print that we got the signal and that we're exiting, and then we do a loop.stop. This is straight from the docs, like what to do when you want to handle. This is terrible. This practice of handling shutdown of an application, it's like the adding signal handlers, that's a good part. That's like actually useful. But what we do with the signals is the problem. We just called stop. And if you do call loop stop, your application will raise a runtime error to be raised wherever you happen to run the loop. Because we all know that your application should explode with unhandled exceptions when you handle a signal and everything goes as expected. The exception lets you know it's working. Okay, nobody thinks like that. If you tell me that you're just going to catch that exception, I'll be paging you tomorrow at 3:25 a.m. If you're not using async.io run, then you need to start the loop again to handle cleanup by yourself. We saw that in the bootstrapping example. And if you are using async.io run, you better be okay with all the tasks being canceled at pretty much the same time. And there's a good chance that you will care. Like, what if you have an async web server, let's say, that runs a status page of your application, and when it's shutting down, you would like to update the status page so you can know that the process is still going and shutting down and know what it's doing. Well, because some of your tasks might take a little while to shut down, and maybe they can update on this page. Well, if you use loop.stop, your web server will probably be the first thing to get canceled. And you're still going to have to wait for your other tasks to finish. One solution is that you could instead cancel a task. This task might be what you're primarily concerned with. Your shutdown logic could be just handled in cancellation flow. You could combine this with maybe a later watcher or a task nursery. Later watcher has a method you can call on the watcher to cancel all the tasks and fall through the context. That's what I use in my method for terminating my applications from signal handlers. And I do that from the non-signaling things. If you combine this with an async context manager and exit stack, you have this like subscribable system that you can handle well-ordered startup and well-ordered shutdown. It all happens in the order you specify. So if you want your web server to be the last thing that gets canceled, you enter its context first. So all the other things have to be canceled and exit, and then your web server shut down. Shutdown logic and signal handling logic should be the same, because most of the time, how else do you shut down your application but sending it a Control-C or a sig term? And even if you have some other non-signally way to shut down your application, you probably want to do the same thing anyway. So just make them the same. Or you could use an event. That might be a solution. Your task could wait on it. They can use it as a looping flag. Multiple places in your code could monitor the same event. It's not as robust as task cancellation and the watcher solution with the async exit stack, but it's better than the blast creator that's created with loop stop, because that provides zero customization about how things get turned off. So we talked about cancellation a few times, so we should probably go over it. So let's spend the next 40 slides to quickly introduce cancellation. Okay, I'm kidding. We're not going to do that, but I am going to go over some of it. Cancellation is tricky, and it's hard, but it's not that hard. Many people screwed up just by ignoring cancellation, either on purpose or out of ignorance. Like this code above, or maybe this code where we still do the same thing, but we're just catching base exception. Or maybe this code where we're still catching cancellation error, but we're just very terrible about it because we're using naked accepts. So if we go back to the code here, so what are we doing here? Like, what were you trying to accomplish? Like, I see patterns like this, and the only time you should ever do something like this is if you have just canceled a task yourself and you're waiting for it to ensure that it cancels. And even then, it's not so simple, as we'll see later. So people generally expect to be able to cancel a task. But task writers never expect their tasks to be canceled. Cancellation is a contract. It's not a clear one, but you agree to it the moment you start writing async IO code. I cobbled together what the contract looks like by just reading through the documentation. It's in a couple different places. Number one, an await statement, any await statement, can raise a cancellation error. It could be somebody canceling you. It could be somebody canceling the task you're waiting on. It could be both. You can be canceled more than once. That's a little weird. You can catch the exception, but you should never ignore it. And always re-raise the exception. When you get canceled, you don't have to exit right now, but you should move towards shutdown. Like async IO run expects that all tasks will eventually cancel because it attempts to do just that before it returns. And as per the documentation, the canceled error exception can be caught to perform custom operations when async tasks are canceled. In almost all situations, that exception must be re-raised. Well, but what about the other ones where you don't have to re-raise it? Well, I guess nobody knows, so we'll figure that out later. It's not hard to comply with the contract. When you get the exception, start your cleanup and stop accepting new work, move towards exiting, and then raise when you're done. This also means you have to stop catching base exception or using empty except clauses with your async IO code unless you're being very careful to check that what you did catch was not a cancel error. Because it is a cancel error, you have to re-raise it in most cases. And the other side of cancellation is easy, right? If you want to cancel a task, you just call cancel. Wrong. That task isn't actually canceled yet. It's scheduled to be canceled for the next time you await something. Yet I see people canceling things and expecting that this is what this happens. For this reason, I have long held the opinion that cancel should return unawaitable. So canceling things correctly is not too hard. You can cancel on a task, but it doesn't actually get canceled until the next event loop cycle. If the task has never been run, then it's canceled without ever the coroutine ever being started. But if the task is already running, the next cycle of the loop will cause a cancel error to be raised from whatever await statement it's currently paused at. And this affects all the things that it's awaiting on as well. So it goes all the way down the chain unless it's shielded and throws in a canceled error. Even then, a task is not considered canceled until it re-raises the canceled error. The docs seem to say it should be the same cancel error. So we do this in the coroutine above. We cancel the task and then we wait on it and catching the exception error, or the cancel exception, because we know it's going to happen. We don't want to raise it because we're purposefully canceling something. But what if the task takes a long time to cancel and someone has come from above you and attempted to cancel you while you're waiting on the task to finish? But you're supposed to re-raise the cancel you got, but we're suppressing it. So maybe it's not as easy as I've let on. So I've come up with this monstrosity. So you can see that what we're doing is we're trying to prevent ourselves from being canceled until the task we are trying to cancel has finished canceling. That's a mouthful. So we check that the task was canceled every time we catch the canceled error. And if we catch one and the task is not done, we save that exception to raise later to complete our part of the cancellation contract. We also cycle the event loop after the task cancels, so we give a chance for the callbacks to get a chance to run. You may notice we also use shield. So this is where this is when we are canceled, we can prevent that the task that we have already sent a cancel message to from getting a secondary cancel while we are awaiting it. Yeah, you could do all this every time you wanted to cancel something, or you could use something like later.cancel from the later package in PyPI. And I will be pushing out a new release sometime tonight to update with this new extended behavior. But let's move on. So you need timeouts. You should use timeouts in your application because in the real world, things get stuck. Now, you may tell me that you have never used timeouts and you don't have any issues. I'd call you a liar, but no. So what are the chances that an async call won't complete in the expected time? Well, in your dev environment, that's 0. Look, we've all heard the lament, hey, it worked in my dev server. Everything works on your dev server because that's where you stuff. But in production is a little different. Everybody has experienced this. Things don't always behave as expected the first time you run it in production. But what you may not know is that running something in production makes your service actively hate you. Not people in general, just you. So during standard business hours, it seems to change based on whether or not you're at your desk. It fails more the moment you step away from your desk. And becomes even more unstable the moment you're out eating lunch with your friends. And not sure exactly how this one happens, but it does. And things also fail more often during weekends than they do on weekdays. Things never seem to fail when you're actually working. There are some obvious modifiers that have been observed on holidays, when you're sleeping, when you don't have access to your laptop, things fail more often. And then later, the later the night gets, the more things fail. So if you're sleeping at 5 a.m. while having forgotten up at work, on a holiday, that's 170%. Wait, you say that's over 100%, Jason, you're not doing probability correctly. Well, at that point, your service has broken all the rules of probability and is going after all the other services in your infrastructure for sport. If you sleep until 10, that's a site-wide incident, and then you are somehow taking down random pieces of the internet, and your CEO is calling you because they have to release a press release. Okay, I've made all that up, but the idea is that your service is going to fail at certain times. You may think it's directly related to you, because it'll just fall on its face at random times. Timeouts are kind of a way to keep things in check when you're not there to manually intervene or to interrupt it when it gets stuck. So look, things fail. Prepare for it. Sometimes things don't raise exceptions when they will never complete. They might raise an exception eventually, but that could be on geologic timescales, not human ones. This is why we have timeouts in software. You have a few choices. There's wait and wait for, but neither are as elegant as the async timeout package from PyPI. Things inside the timeout context get canceled if they run too long. And outside the context gets raised a timeout error. When you are waiting for something that could be delayed, consider adding timeouts around the code. When you don't want to have to be woken up in the middle of the night, figure out why your service is doing nothing at all. In our example above, we are using nested timeouts because the request timeout we should plan to retry them when they time out. And how long we should attempt to retry them, that's a case of a budget we've set like 100 milliseconds. So that they should only ever take 100 milliseconds total if they have to keep retrying. So look, shit happens. Try to make the best of it. Asyncio can be a powerful tool, but used poorly will cause you lots of pain. So let's wrap up this talk. So in conclusion, never assume intent or violate ownership expectations. Nested event loops is a bad idea. If you want logical startup and shutdown, use asyncio context managers and async exit stacks. Tasks fail or sometimes never complete. Use timeouts and handle your exceptions. I've had people tell me that cancellation is too hard. Look, it's not that hard, and it's not that painful to set up. It's definitely better than being paged in the middle of a cold night while you're sleeping. I suggest asyncio run because it's the best bootstrap we have. Even though it raises exceptions, it's awesome because I'd rather know that you're attempting to run an event loop that I can easily put in executor without having to worry about threads getting default event loops. That's it. Thank you for coming to my TED Talk. Any questions? Questions will be out in the hallway.